Completing the square, actually, we're going to see in 7.2, is where the quadratic formula comes from, actually. The technique is very useful that we're going to use. It's good algebraically to practice this. And then just to practice actually solving equations. It allows you to solve any quadratic equation, even if it can't be factored. Okay, so far you've talked about what? Where we can factor stuff into like difference of squares or just regular factoring. Sometimes we've talked about perfect square trinomials. In this case, we're going to say, you know what? It doesn't matter what kind of quadratic we have, because with completing the square, we can solve it independent of its nature. It doesn't matter, again, if you have the actual factorization available. So let's take a quick look at what we're going to do. So this was the general form we've looked at, right? We've said that, you know what? If we can take an equation that has some sort of a quadratic in it and write it like this, we could say that P and Q are the solutions to that equation, right? When we solve this, we get P and Q. But we're also going to note that we're going to look at equations like this that are in this form. X squared is equal to R. And what have we done in this case? We've taken the square root of both sides and we put a plus or minus on this side. So just to recall what we've done already. Okay, we're going to utilize this information in this section. So let's start with the first example. So as I've done in the past, I've worked you up, right, from one that's easier to as they get more difficult progressively. So part A is the first one. Now, can I get a suggestion as to how to solve part A? And there are more than one way to do this, so there's not just one correct answer. Regina, what do you think I should do?
You like do x minus 2 times x minus 2, and then you solve that and bring over the 3 and set it equal to 0, and then solve from there.
All right, so we got x squared minus 4x plus 4 equals 3, which becomes x squared minus 4x plus 1 equals 0. But now at this point, unfortunately, I can't factor, right? Unfortunately, I can't factor this. There's nothing that works to make this factor. There's no numbers that multiply to give me 1 and add up to negative 4. So that's the technique we would approach with. We would multiply it out, and then we would move everything over to one side, get a 0, and then factor. Doesn't work. Suggestion, what else can I do? What else can I do for this problem? How else can I approach solving part A? And I'll give you a hint, it doesn't involve multiplying out the x minus 2. So we don't need to take that approach. We're going to show another method to do it. What else could I do?
Wait, could you square both sides?
Square root, right?
Yeah,
square root?
Yeah.
Okay, so what does that become? If I square root both sides to start instead. Get Alex?
It would be x minus 2 equals square root of 3.
Missing something? It's a square root of 3 for sure, but what else? Plus or minus, right? And this is where it's going to come into play. Remember, how many answers do we get when you solve a quadratic? 2. Plus or minus is going to make a big difference here. Continue, Alex.
And then...
I want to isolate x, so...
Yeah. So then just move 2 onto the other side.
And look what I'm going to do. I want to point this out. Make a big point in your notes about this, please. And the reason I'm pointing this out is because I don't know if you guys know this, I do a lot of test prep tutoring outside of school. So like for SATs and stuff like that. And when I work with students, I find that, I don't know why it is, but a lot of people put the number on the other side of the actual radical or the plus or minus term. So I'll notice a lot of students taking this and they say, okay, I'm going to add 2 and I'm going to add 2. And then you know what they write instead is they write this. They write x equals plus or minus 3 root 3 plus 2. They'll put the plus or minus here, right, as a plus or minus root 3, and then they'll add 2 to that. So yeah, you're still going to get 2 answers here. Plus or minus, that's a little bit ugly the way that looks. But the problem is that you don't see it as obviously. When it's written like this, right, 2 plus or minus root 3, it's obvious that you have 2 physical answers. It's 2 plus root 3 or 2 minus root 3. That's what the answer to this problem is. Again, 2 plus root 3 or 2 minus root 3. And as we just said a minute ago, because this is a squared equation, we will get 2 answers. Again, a squared equation, we will get 2 answers for. All right, again, I'm just pointing this out because this is not really as obvious that you have 2 answers. Okay, you don't put the number on the right side, you're always going to put the number on the left side of the plus or minus. Again, whatever you're moving over at the end will always go on the left side of the plus or minus. It's not wrong the other way. It's just not as obvious as to what you should do next if you do it that way. Alex?
So then we just do like two different scenarios and one where it's negative and then use I?
So in this case, because we're not looking at a negative, we're not looking at a negative under the radical, we don't have to worry about I here.
Okay.
The negative is outside the radical. So this number, 2 minus root 3, is some decimal. I'm sorry, 2 plus root 3. And then 2 minus root 3 is some other decimal. I'm not asking you to get those numbers right this moment. When we graph this, which we will, later in chapter 7, we'll do a lot with graphing with quadratics. It's good to have a decimal estimate, because if I'm looking at the x-intercepts, which is what these are, I want to know where they're going to be on the x-axis. 2 plus root 3, where is that on the x-axis? I mean, yeah, root 3 is definitely below the number 2, so root 3 is probably like, I don't know, 1.7 or something, who knows, right? What does root 3 come out to be approximately? You add that to 2 and then you get 3.7. But the decimal approximation is useful when you're graphing, not as useful when you're solving the actual equation. Okay, so again, you can get a decimal or an approximate decimal for each of these and list them if you'd like.
And also you want to remember that onto the third.
Oh, yes, I did. Should have started with that. No, that's all right, because I just did this. Let me see how we're doing with time after this example, and I'll go back to that. Thank you, Alex. Definitely don't forget that. Remind me again, please. So the second example is very similar to the first one. It's very similar to the first one, but we noticed that there's an extra step along the way. That's the only difference we're going to have. So when we did the first one, we ended up getting 2 answers. With part B, we're also going to get 2 answers. Let's take a look at that now over here. So let's take the same approach. We could multiply it out, which does work sometimes, but if it's not factorable, multiplying it out is a waste of time. So when we see a binomial squared from now on equal to some number, let's go ahead and just take the square root to start. Okay, so let's do that again. Let's take the square root of both sides. So the left side becomes 2x minus 5. The right-hand side becomes plus or minus radical 8.
Would you write it, could you write it as 2 square root 2?
Yeah. This is one of those times you definitely want to reduce your radicals. Absolutely reduce your radicals whenever you can.
But would you put the plus or minus in front of, the 2 or the square root?
You would, because remember, root 8 is really 2 root 2. And the plus or minus is affecting the whole thing, right? So it's affecting the entire thing there. Oh, this is not... Oh, there it goes. Okay. Thought it was responding for a second. Then we're going to get rid of the 5 and get rid of the 2. We get rid of the 5. How do we get rid of the 5?
Yeah,
Yeah, and how am I going to add it? Where am I going to make it?
put it in front of the plus or minus 2 square root 2.
Okay, and that equals 2x. And then finally, what do I have to do at the very end? I want to get x this time, so there's an extra step here, right? There's one extra step. That's all it really is. What do I do to end it? Yeah, just divide by 2. Now, when I divide by 2, I can write the whole thing over 2, or I'm going to take the approach that we've been taking, which is putting each of them over 2. Thanks, Luca. So I have 2 root 2 over 2 there. And the 2 root 2 over 2, these 2's are going to cancel each other out. 5 over 2, just leave it as 5 over 2. You can write 2.5 if you want, but what's the difference whether I write a fraction or a decimal here? So if I want to give an answer, I would say x equals 5 halves plus or minus root 2. Okay, 5 halves plus or minus root 2. Yeah.
And so when you divide by 2, you don't divide into the square root 2, right?
Correct. Remember, outsides divide outsides, insides divide insides. If I had divided both sides by radical 2, then the radical 2's would have canceled each other, and the outside 2 would not have canceled. Yeah? Very good. Okay, that's a great question because I see that mistake all the time, right? So Isabella's asking a good question here to recognize that the 2 that you're dividing by does not cancel out this part right here. Okay, this part that I'm pointing to with the radical 2 does not drop off. You cannot cancel these because this is a 2 on the outside and this is a 2 on the inside. How about part C? Part C says the following. Quantity x plus 1 squared is equal to negative 4. Right away, what kind of an answer will I have here? Good. Not irrational, imaginary. Yeah, unreal is fine. She said unreal. It's an unreal answer. Very good. There's a negative that I'm going to take a square root of here right away. I start again the same way. Take the square root of both sides. This becomes plus or minus radical negative 4. When I have a negative under the radical, what do I automatically do? Yeah. So this becomes plus or minus I root 4. But root 4 is just simply 2. So this is plus or minus I times 2. I'm going to write it as 2 times I. Okay, like we've been doing already. I'm going to write it as 2 times I times 2, same thing. Now, this part seems to throw a lot of people for a little bit of a curveball here. How do I get rid of 1? How do I get rid of 1? You subtract it. But what's the definition of subtraction? Beginning of the year. What do we define subtraction as? Yeah, you're adding the opposite. So instead of subtracting 1, because if you subtract 1 again, 9 out of 10 students are going to take the 1 and they're going to put a minus 1 on this side, which is logical, and that's probably what a lot of you did already, and that's totally okay. But to remind yourselves of what's happening here, I'm going to add negative 1 to both sides. Is that clear what I'm saying? It just makes sense logically, because the definition of subtraction is adding the opposite. So I'm going to add negative 1 to both sides. You don't have to write it. I'm writing it this time, but you don't have to write it from this point on. And this will become x equals negative 1 plus or minus 2I. So I don't want you to think about subtracting in this process, because I do want you to have whatever this constant is in front of the plus or minus, or to the left of the plus or minus. Again, this constant here should always move to the left-hand side of the plus or minus. And the only way to do that logically is to move a positive 1 over as a negative 1. And remember, you can always do this. Whenever you move a whole term over from one side of the equation to the other, just negate it. Simply negate it. So I'm currently adding 1. I'm still going to add something, but I'm going to add instead, I'm going to add negative 1. And that's the same thing as putting a negative 1 in the very front. Okay? Same exact thing. They're identical, but I'm telling you now that this is the better way to write it. This is the way you're always going to see it. This is in A plus BI form. Like we've been talking about from the last section, we have a real part and we have an imaginary part. Or we have a rational part, and then this is where the radical occurs for the irrational roots we're going to get. Okay, we're going to separate them like that every time. How about the last part? Part D, the challenge for this one. Part D is the challenge. I want someone to step me through what the process is I should take. And this is x squared minus 4x plus 4 is equal to negative 5. And again, you could solve this by moving the 5 over and trying to figure out roots, but there's a better way to do it. Sebastian, what do you think?
This is back to x squared minus 4x plus 4 should equal x minus 2 squared.
Very good. And he already jumped to the next line, which is what we're going to get to. Very good. So factoring the left-hand side works really nicely sometimes. And what we're going to do today is come up with a method that always factors into the same factor. Our goal today is to come up with something where we can always have a perfect square. Hence the name, completing the square. That's where the name comes from. We always want something with a square term that is a factor that is squared. So we're going to come up with a method today to always make this work. For now, I made the problems work. But when we get to example 2, we'll develop this method a little bit better. And then we go about solving this the exact same way as we've solved parts A, B, and C. We go ahead and take the square root of both sides. I cannot do anything with this besides take out the I. I can't take the square root of 5. It's not going to be broken down further. So I can take out the I. Okay? And when you have a radical, I know we talked about this yesterday more. I think you asked this question actually. This I is on the left-hand side. It could also be on the right-hand side because we want an A plus BI form. But the problem with radicals is that traditionally you put the values in front of the radical, not usually after. So this is one of the times where writing it either way is okay. But the 2 that we're going to move, right, this 2 here, let's add this 2 over and put it right in front. Right, we'll add the 2 right in front. So we'll get x equals 2 plus or minus I root 5 or root 5I. Either way is acceptable in this case. But again, getting 2 answers. 2 plus I root 5, 2 minus I root 5. Now, we've gone over this idea already that the roots of an equation are the same thing as the zeros of a function or the x-intercepts of a function. So if I get answers like this, how can I graph these as x-intercepts? How do you graph an imaginary number as an x-intercept? What do you think is going on with these graphs? What do you think is happening with these kind of graphs? You don't. What do you mean by that, Maura? Give me more. So what could this graph look like, hypothetically? It's squared, so I know it's a parabola. We haven't studied them yet, but you guys have seen them in middle school, at least the shape. So it is a parabola. So where would the parabola lie on this graph to show that there are no real roots or no real x-intercepts?
Would it be like cross? Never mind. I was gonna say it would be like crossing the 0.
Not the 0. Not the 0.
Is it nowhere?
What do you mean nowhere?
If not, you can't graph it. Because
You can graph it. You can graph it.
Wouldn't like the vertex be either above or below the x-axis?
And it would only open up if it was above and open down if it was below. So this is going to be a shape of a graph that looks maybe like this, or like this, or like this, or like this, or like this. But the idea is that if the function is above the x-axis, it's going to open up. If it's below the x-axis, it's going to open down. And when this happens, you have no x-intercepts anywhere. Sure, you can have a y-intercept, but there are no x-intercepts for any of these example functions. These are examples that have roots that are imaginary. We're going to get to quadratics in a little bit where the roots are imaginary, and that's what they will look like generally. Okay, we're going to reinforce this. We will, because we're going to do a lot with graphing, but I want you to see the connection already. Start to see the connection being made. Yeah? So let's come up with a general focus that we can use. So let's use example 2 to do this. And let's go through the process here and say to ourselves, how can we create a perfect square? How can we create a perfect square? So I'm going to ask you this question. I don't want the answer of the whole problem. I don't want the roots. I'm going to ask you this question. What number should 3 be? See the number 3? What should we change 3 to make it work so that I can factor this and that both factors will be the same? What should I change 3 to so that when I factor it, both factors are the same? Jot it down real quick. Try to get an idea. Maybe try some stuff. Try numbers for 3. Instead of 3, put a number in its place. Put something else that might factor, that might work. I want you to think about it. I know a couple of you picked up on it right away. Okay, but what do I want to change 3 to so that it will factor evenly into the same factors? And if you're not sure, think about the number 10 in the middle. How can you get the number 10? That comes from adding the 2 values, doesn't it? The middle term is the sum of the factors, and the last term is the product. So what numbers add up to 10 that are the same numbers? What number plus itself gives you 10, literally? 5. So we want the factors to be x minus 5, x minus 5. Is that clear? Look at the b value. The b value is negative 10. The only way to get a b value of negative 10 is to have factors of x minus 5, x minus 5. So if the factors are x minus 5, x minus 5, what should the c term be at the end? What should this value 3 actually be?
25.
25. Okay, and I saw a couple of you get it right away. So I need this to become a 25. That's what I want it to be. So there's a technique we're going to use, and the technique is very simple. Start by getting rid of the 3. Move the 3 over to the other side. So let's go ahead and do that. All right? So let's get rid of whatever c is. You can do this 2 ways, by the way. If you look this up online, some teachers suggest that you just leave the 3 over here and figure out what number you have to add to 25 to make it work. To add to 3 to make it 25, which is 22. And that's fine. I prefer doing it this way. I will explain why I'm right. I'm actually right. That's not about, the other way works, but my method is better. And I'll tell you why as we get to it. Because there's going to come a nuance in the second part where doing it the other way causes issues. So why teach it the other way, right? When it's going to cause an issue down the road. Do it this way and you will never have a problem with it. So take this number and take half of it. Like we said. We said, what was half of 10? And that was the -5. And then Julia said, well, what number has to go here? What did you do with -5? You just took that number and you squared it, and that gave you 25. So let's go ahead and add 25 to both sides of the equation. Remember, what I do to one side of the equation, I must do to the other. And what that does in the end is that it does yield the 22 that we were talking about, right? Look at the right-hand side now. The right-hand side becomes 22. So it's the same thing, as I said again, as adding 22 here and adding 22 here. You can add 22 to both sides to start and you'll get the same thing. And that's fine right now. But again, when you get to more difficult problems, it's not as easy and it won't work as well. So for now, trust me on this one. When I factor this, as we said, we're going to end up with these factors. And then this is always going to become squared every time. That's the idea or the reason why we are doing this method, which is called completing the square for a reason. So that's the process we're going to undergo. And then we can solve the same way we solved example 1. Yeah? We take the square root of both sides. X minus 5 equals plus or minus root 22. Add the 5 over. X equals 5 plus or minus root 22. X equals 5 plus or minus root 22. So if we generalize, there's a way to generalize this on the map. Okay, we'll talk about the general steps that we're going to utilize. And I'm going to use an example for this one that, again, causes a bit of a complication in the system that we're going to look at. So let's start with the general example of 2x squared. We'll put the example on the right side. I'll put the steps on the left. Minus 16x plus 30. Okay, let's start with this example here. So, notice what did I introduce with this example that wasn't in the other examples? There's an a term now, right? The 2, that's the leading coefficient. So the first, and I made this work out so that they're all even on purpose, because this is still the easier level. We'll get to the harder one in the next, but I want to give you the general steps. So the first step you should take is to clear out A. Is to clear out A, always, a GCF. Even if it's not a GCF though, even if these were odd, right? Even if this was 31, divide everything by 2. I leave this as 31 over 2. So always start by dividing all terms by A. Divide all terms by A. That'll give us, in this case, x squared minus 8x, and in this case, plus 15 equals 0. So divide by A. So if we're writing steps, I guess I can write all the steps, but can I just say them and you guys can write them? Okay, step 1 would be divide by A. Step 2. What do we say we're going to do after that?
Move C over.
Yeah. So move the new C over. I'm going to put C in quotes. The reason I'm saying that is because the C value is actually 30, right? Are we all clear that C is 30 here? In this problem, C is 30. It's just that we divided by A, which can give us like a new C value. So move the new C value over, which is the 15. And step 2 will look like this now. Step 3. What's step 3? How do I find that perfect square? What do I have to tack on that little space? I left it blank for a reason. What do I have to put here that makes this problem work?
Is it the half of term b squared?
That's very good. Well done and well stated also. So you take whatever is here, term b, the new term b, right? The original term b is really 16. But now that we divided by 2, b is 8 or negative 8. Take half of it and square it. So add b over 2 squared to both sides. Take the quantity b over 2 squared and add it to both sides. So half of negative 8 is negative 4. That number squared is 16. So I'm going to tack on 16 to both sides of the equation. And then on the left-hand side, although it's obvious to you guys right now, although it's obvious, the factoring is not always going to be as easy as this. This example, yeah, it's x minus 4, x minus 4. And that's fine. And then on the right-hand side, it becomes actually a 1. But pick up on something. I want you to recognize this. Write yourself a little note. The factor, this value inside the factor, will always be whatever half of this was. Every time it's going to work out that way. So if this number is a little more, we're going to see ones in a minute where they're all fractions. And you're like, how the heck do you factor this, right? Whatever this is, right here, didn't you have it and then square it to get this number? The reason you halved it was because you wanted half of it to appear in each spot. And then when you multiply these, that's where the square part comes in. So whatever the b value is, half of the b value will always become the factored form. So this will always look like x plus or minus whatever b is, and half of it squared is equal to some number. This will always be the general form that you're going to end up with. So whether it's plus or minus depends on the original problem, because the original was minus, I carried down a minus, but it was whatever b was divided by 2 that goes there, and then that value becomes squared. Again, because this is really x minus 4, bless you, squared equals 1. How about you? Okay? It's always going to work out that way, that whatever the factor is will be half of the b value as the numerical term added or subtracted from x. And then the process is the same. The next step is take the square root of both sides. Right? Take the square root of both sides and solve for x. And remember, when you solve, you're going to get 2 answers for this. You're going to get 2 answers every time. So look at an example with these general steps now. An example that involves clearly something that might not be as easy as the other one from before. So let's take a look at one that involves an imaginary setup. If I want to take a look at this one, is there any a value? No, so I don't have to worry about it. So let's start by getting rid of the 13. Half of 6 is 3. 3 squared is 9. So I'm going to add 9 to both sides. On the next line, this becomes x plus 3 quantity squared. This becomes negative 4. We're going to square root both sides again. Get x plus 3 equals plus or minus the square root of the square root of negative 4. And the square root of negative 4 is just, from yesterday, the square root of negative 4 simply becomes what? 2i. And then move the 3 over by adding a negative 3 over to this side. Okay, add a negative 3 over to the right-hand side. So the process is very simple. It's just that the problem can become more difficult. Okay, the problem can become more difficult. Let's do one. I think the last one involves fractions. I'm pretty sure I made it through that. Let me see. Yeah. Let's look at the last one here, okay? We're all for today. This last one involves a good amount of fractions because of the a value. Because of the a value. So when I divide everything by a, some students in the past like to go to decimals, and decimals get so messy because you know what? Have fun squaring 1.25 or 6.75. Have fun, seriously, squaring that and keeping track. If it's a fraction though, and you square a fraction, just square the top, square the bottom. Isn't it easy? Right? 1.25 squared, what is it? Go. No, but if you think of 5/4, what's 5/4 squared? 25/16. You're done. And 1.25 is the same thing as 5/4. So when you write these, write yourself a note here, leave everything as a fraction. Leave everything as a fraction here. So let's divide by a first. So divide by 2 everywhere. Right? Divide every term literally by 2. When I do that, we're going to end up with here y squared plus 5 halves y minus 3 halves equals 0. Again, I'm leaving it as a fraction right now because I know in a minute I'm going to have to do some squaring. Now I'm going to move the c value over to the right-hand side. And again, I'm leaving it as a fraction. So, what goes here? What goes here? Go.
25/16.
Yeah, it worked out. That was a coincidence. I didn't mean to pick that number again. Yeah. 25/16. Where is that coming from? Go.
Half of 5 over 0, so it's 5 plus squared.
Yeah. Little trick. I find this every year students have trouble with this. To have a fraction, just double the denominator. When you want to have a fraction, double the denominator. I know, it sounds like it's common sense, but believe it or not, a lot of people have trouble having this. So to have this, it becomes 5/4, right? Just double the denominator, make that a 4 in your mind. And then you have to square that, right? So we need to take 5/4 squared. Again, half of b, I'll write it down over here, is 5/2 divided by 2, which is the same thing as 5/2 times 1/2, which is really 5/4. And then we have to take that quantity and we have to go ahead and square that still. So we take that and square it and add it right here. So again, you're going to add 25/16 to both sides. Now, this is where I was saying the factoring looks way, way more confusing than everything we've done. But, I think Isabella mentioned it to us here, we're going to just literally take half of this number and it's going to become the factors every time. So yeah, this looks complicated to factor this. It's not though. This is actually quite simple to factor. It's y plus 5/4 and y plus 5/4. Whatever the half of b was that we used to square to come up with this number is always what's going to end up being in my factored form. So my factored form of this, again, will be y plus 5/4 and y plus 5/4. It's always going to repeat itself. And that's where the y plus 5/4 squared is going to come into play. So again, this number, not only does it get squared and added to both sides, you actually use this number here in both spots as well. So it's important to recognize that half of b is going to show up here squared, but also here. How about the right-hand side? Obviously, what do? When we're combining fractions, we have to have a common denominator, right? So let's make it 16. So multiply by 8. This is going to be 24 over 16. Multiply by 8 over 8, I'm saying, obviously. Multiply the top by 8, multiply the bottom by 8. 24 over 16 plus 25 over 16.
49.
And look at that. I don't think it's a coincidence, right? What do you notice? This is a perfect square. Okay? The problem was made in such a fashion that it was made to have that. It will not always happen. Write yourself a note if you want to, okay? This will not always be a perfect square. And you just take the square root and you'll leave it as a radical. So maybe this will be 49 over 15. And your answer will have radical 49 over 15 in it. But it happens to be nice that it works out with a perfect square. So let's go ahead and square root both sides. And the square root of 49 is simply going to give me a 7. And the square root of 16 is going to give me a 4. And then how do we get rid of the 5/4? Remember, it's a positive, so I'm going to add a negative 5/4 right here. Again, adding negative 5/4 right here in front of the plus or minus. So would you leave an answer like this? Would you leave an answer like this? I probably wouldn't. I'd probably come up with the answer because look, no imaginary term, so no I. If there's an I here, you can't combine it. If there's a radical 3 on the end, then you have a rational plus an irrational cannot be added together. But these are both rational terms with a common denominator. Definitely combine them. So negative 5 plus 7 all over 4. Let's do the first one. Negative 5 plus 7, is 1/2, good. And then negative 5 minus 7 all over 4. So for those that are confused of where the answer is coming from, let me just show. So we have negative 5 over 4 plus 7 over 4, and then negative 5 over 4 minus 7 over 4. So Valentina gave us the first one. This becomes a 1/2. Right? Because this is going to become just simply 2 in the numerator over 4. But then this side, we're going to get the negative 12 really from this, right? This is negative 5 minus 7 is negative 12 over 4. So we're going to get a negative, negative 3 here. So we get two integer answers, or two rational, I should say, two rational answers. You want to write, take your question, one more thing. If you want to write this down, you can say, whenever your answers are purely rational, it means the original could have been factored, actually. We could have set the original equal to 0 and factored the original problem. This would have been an AC method factoring, though, right? You see that? If you go back up to the original and look at the top, it was 2x squared with some other numbers. You would have had to use AC method. But this could be factored because the answer is purely rational. There's no imaginary part, and there's no square root part of the answer, so it must have been able to be factored at some point.
Where'd you get the 49 over 16?
The 49 is the 24 over 16 plus the 25 over 16. Look at the previous step. It's off the screen, that's why. Can you see the step up here, 24 over 16? I created 3 halves. I changed 3 halves into 24 sixteenths on the right side there. The reason for this, right here, 24 over 15 plus 16, the 16 carries down, 24 and 25 gives you the 49. Just common denominator along the way. Okay, go back through. Hey, don't forget, guys, to work on this stuff, please, over the weekend. Okay, you do have homework for this.